Hello students, welcome to lecture 7 of chemical equilibrium. In previous class we discussed about homogeneous equilibria and heterogeneous equilibria. In this lecture our topic is applications of equilibrium constants. The important features of equilibrium constants. Number 1, expression for equilibrium constant is applicable only when the concentrations of reactants and products attained constant value at equilibrium state. So equilibrium constant is applicable only when the concentrations of reactants and products attained constant value at equilibrium state. And number 2, the equilibrium constant value is independent on the initial concentrations of reactants and products. So equilibrium constant is independent on the initial concentrations of reactants and products. Number 3, equilibrium constant is temperature dependent. That equilibrium constant is temperature dependent. So independent on the initial concentrations of reactants and products, but dependent on the temperature. And number 4, reverse reaction equilibrium constant is equal to inverse of forward reaction. Reverse reaction equilibrium constant is equal to inverse of forward reaction. Inverse of forward reaction. Let me take one example. H2 plus Cl2 equilibrium 2HCl. So this is the forward reaction and this is the reverse reaction. For forward reaction, equilibrium constant K is equal to, for forward reaction, equilibrium constant K is equal to the concentration of products divided by concentrations of reactants. So HCl concentration with coefficient 2 power 2 divided by reactants concentration, H2 concentration and Cl2 concentration. For reverse reaction, equilibrium constant K dash is equal to, in that reverse reaction, HCl is the reactant and H2 plus Cl2. So these two are the products. So products concentration, H2 concentration and Cl2 concentration divided by HCl concentration power 2 is equal to, so this is the inverse of forward reaction. In that forward reaction, in numerator HCl power 2, in the reverse reaction in denominator HCl power 2, and in this, in denominator H2 concentration and Cl2 concentration. In reverse reaction, the H2 concentration and Cl2 concentration in numerator. So it is the reverse of this one. So we can take 1 by K. So reverse reaction equilibrium constant is inverse of forward reaction 1 by K. Next, number 5. If we have chemical equation and it multiplying or dividing entire chemical equation by a certain number, then the new equation equilibrium constant would be related to the original one. Let me take one example, H2 plus Cl2 equilibrium 2HCl. It is a original equation. For this original equation, the equilibrium constant K is equal to products concentration, HCl concentration, quotient 2 power 2 divided by, and the reactants concentration, H2 concentration and Cl2 concentration. This original equation multiply by 2. This original equation multiplying by 2. Then we are getting a new equation, and that new equation equilibrium constant would be related to the original one. This equation multiplying by 2, then the new equation here 2H2 plus 2Cl2 equilibrium 2 into 2HCl. This entire equation multiplying by 2. Then we are getting a new equation. This new equation equilibrium constant K double dash is equal to products concentration, HCl concentration, and with quotient 2 into 2 4 power 4 divided by reactants concentration, H2 concentration with quotient 2 and Cl2 concentration with quotient 2 is equal to, we can write that HCl concentration power 2 divided by H2 concentration and Cl2 concentration, and all equation power 2. It is equal to this one because here 2 into 2 4 and here 2 H2 power 2 and Cl2 power 2. That is equal to HCl power 2 divided by H2 concentration and Cl2 concentration. It is equal to K. Then we can take K and power 2. So here K double dash is equal to K power 2. So that new equation is related to the original one. So these are the important features of equilibrium constants. Next one, predicting the extent of a reaction. The numerical value of the equilibrium constant indicates extent of the reaction, and equilibrium constant does not give any information about the rate of the reaction. So equilibrium constant numerical value indicates extent of the reaction, and equilibrium constant does not give any information about the rate of the reaction. And the magnitude of Kc or Kp is directly proportional to the product's concentration and inversely proportional to the reactant's concentration. So that Kc or Kp is directly proportional to the product's concentration. and Kc or Kp is inversely proportional to the concentration of reactants. If Kc is greater than 10 to the power of 3, the products predominate over the reactants. Then the reaction almost completed. So if Kc is more than 10 to the power of 3, the reaction almost completed. Example number 1, H2 reacts with O2 at 500 Kelvin, and here the constant, equilibrium constant Kc is equal to 2.4 into 10 to the power of 47. It is more than 10 to the power of 3. So the reaction almost completed. Next, example number 2, H2 gas react with Cl2 gas, equilibrium 2HCl gas at 300 Kelvin, and here the equilibrium constant Kc is equal to 4.0 into 10 to the power of 31. Next, example number 3, H2 gas plus Br2 gas, equilibrium 2HBr gas at 300 Kelvin, and here the equilibrium constant Kc is equal to 5.4 into 10 to the power of 18. So in all these reactions, the products predominate over the reactants. Then the reactions almost completed. Here the Kc values are more than 10 to the power of 3. If Kc is less than 10 to the power of minus 3, if Kc is less than 10 to the power of minus 3, so the value is very less. The reactants predominate over the products. The reactions proceeds rarely because the Kc value is very less. Let me take examples. Example number 1, decomposition of H2O into H2 and O2. So 2H2O equilibrium 2H2 plus O2 at 500 Kelvin. So here Kc is equal to, equilibrium constant Kc is equal to 4.1 into 10 to the power of minus 48. And example number 2, N2 gas plus O2 gas, equilibrium 2NO gas at 298 Kelvin. So here the equilibrium constant Kc is equal to 4.8 into 10 to the power of minus 31. So in these reactions, the reactants predominate over the products. And if Kc is in the range of 10 to the power of minus 3 to 10 to the power of 3, between this range, appreciable concentrations of reactants and products are present. Let me take example 1, H2 plus I2 equilibrium 2Hi at 700 Kelvin, and the Kc, equilibrium constant Kc, is equal to 57. Here at this point the Kc value is 1, and here the Kc value is 10 to the power of minus 3, and here the Kc value is 10 to the power of 3, and at right side the value is more, and at left side the value is less. If the Kc value is very less, means almost negligible, the reaction hardly proceeds. If the Kc value is very large, extremely large, the reaction almost completed. And the Kc value between the range of 10 to the power of minus 3 to 10 to the power of 3, the reactants and products at equilibrium. So this reaction equilibrium constant Kc is 57, means in the range of 10 to the power of minus 3 to 10 to the power of 3. So the appreciable concentrations of reactants and products are present. And let me take example number 2. Example number 2, N2O4 gas, equilibrium, 2NO2 gas at 298 Kelvin. For this reaction, the Kc, the equilibrium constant Kc, is equal to 4.64 into 10 to the power of minus 3. So it is neither too small nor too large. Hence, equilibrium mixture contain appreciable concentrations of reactant and product, N2O4 and NO2. And next one, predicting the direction of the reaction. The equilibrium constant helps in predicting the direction of the reaction at any stage, means specifies whether to move forward or backward. So for this we have to calculate the reaction coefficient Q. Reaction coefficient Q. Qc is with the molar concentration and Qp is with the partial pressure. So it is molar concentration. Qp is with the partial pressure. Let me write one general reaction. Reactant A with the coefficient A, and the reactant B with the coefficient small b, equilibrium, and the product C with the coefficient C, and plus the product D with the coefficient D. For this equation, the equation coefficient Qc is equal to products concentration, C concentration power C, and D concentration power D, divided by reactants concentration, A concentration power A and B concentration power B. In this reaction, if Qc is greater than Kc, the reaction will proceed towards reactants until attain equilibrium. So Qc is greater than Kc, the reaction will proceed towards reactants. So these are the reactants, and here products. Towards the reactants means reverse direction. If Qc is greater than Kc, the reaction direction is reverse, means products to reactants until attain equilibrium. Next, if QC is less than Kc, the reaction will proceed towards products until attain equilibrium. So here reactants and here products. So the reaction proceeds towards the products, means forward direction. So if QC is less than Kc, the reaction direction is forward from reactants to products. And if QC is equal to Kc, the reaction already at equilibrium. Let me take one example. H2 gas plus I2 gas equilibrium 2HI gas. So here Kc is equal to 57 at 700 Kelvin. Suppose the molar concentrations H2 molar concentration, H2 molar concentration, subscript T. The subscript T indicates concentrations measured at certain time. So H2 concentration T, molar concentration 0.10 m, and I2 molar concentration, I2 concentration T is equal to 0.20 m, and HI concentration T is equal to 0.40 m. So here QC is equal to the concentration of products divided by concentration of reactants. So HI concentration, the quotient 2 power 2 divided by, and H2 concentration and I2 concentration is equal to that HI concentration is 0.40, 0.40 power 2 divided by, and H2 concentration 0.10, 0.10 into I2 concentration 0.20, 0.20 is equal to, if you do this calculation, we will get 8.0. So here QC is equal to 8.0. So that QC is equal to 8.0 is not equal to equilibrium constant Kc is equal to 57. So the mixture is not at equilibrium. At this stage, more H2 and I2 react to form more HI until attain QC is equal to Kc. Therefore, the reaction proceeds towards products, means H2 plus I2 towards products HI. So it is a forward direction. So that QC is not equal to Kc. QC is 8, but the Kc is 57. So the QC is not equal to Kc. Means here QC is less than Kc. Means here QC is less than Kc. The direction is forward direction from reactants to products. So here from reactants to products. So the QC is useful in predicting the direction of reaction by comparing QC and Kc values. So here if QC is less than Kc, the net reaction net reaction goes from left to right. Left to right means forward direction. And if QC is greater than Kc, the net reaction goes from right to left. Right to left. Right to left means reverse direction. And if QC is equal to Kc, no net reaction occurs. No net reaction occurs. So here the QC value is less and Kc value is more. Here the reaction goes from left to right, means from reactants to products, means it is a forward direction. And here the QC value is more and the Kc value is less. Consequently, the reaction goes from right to left, means products to reactants. So it is a reverse direction. And the QC value and Kc values are equal. The reactants and products are at equilibrium. So this is about predicting the direction of a reaction.